So in this video, we're going to talk about the formal definition of a limit. This is also called the epsilon delta definition of a limit. So this little E symbol is an epsilon. And this little kind of D symbol here is a delta, and these are Greek letters. So if we let epsilon represent an arbitrarily small positive number, so that's that arbitrary closeness that we talked about to L, let's define what it means mathematically for f of x to become arbitrarily close to L. So this means that f of x lies in the interval between L minus epsilon and L plus epsilon. It's between those two values. F of x is equal to L, give or take an epsilon. So what this means is that f of x is between L minus epsilon and L plus epsilon. Now, if I wanted to move things around a little bit, I could come into all three pieces of this inequality and I could subtract an L. So this tells me that negative epsilon is less than f of x minus L, because that cancels, which is less than epsilon. And another way to write this is that f of x minus L is less than epsilon units away from 0. So the absolute value of f of x minus L is less than epsilon. We're going to take a very similar approach and talk about what it means for x to approach c. So the way that we say this is that there exists a very tiny number delta greater than 0, and this is the lower case of that triangle delta that we talked about earlier, such that x is in the interval either c minus delta to c, or x is in the interval from c to c plus delta. Now, one thing that's different about the idea of f of x being arbitrarily close to L and x approaching c is that in the first half we assumed that f of x could actually be equal to L. We held that possibility open. In this one, we're assuming that we don't have to worry about the case where x actually equals c. So it may or may not be the case that x could be c, but we're just not even worrying about that. So if you take each of these intervals independently, the first one, c minus delta to c, says that x is between c minus delta and c, and the second one says that x is between c and c plus delta. So I'm going to take the same approach that I did before. I'm going to subtract c from all three parts. So over here I get that negative delta is less than x minus c is less than 0. And if I do the same thing over here, I get that 0 is less than x minus c is less than delta. So this gives me the idea that the absolute value of x minus c is more than 0 units, is more than 0, but it is less than delta. So we're more than 0 units away from 0. We're not exactly 0, but we are less than delta units away from 0. So this leads to the following inequality. So this is one part of the definition, and this is going to be the other part of the definition. And that's where they come from. So keeping that in mind, this is the definition of a limit. We talked about an informal definition earlier, but this is the formal definition of a limit. It's also, if I refer to the epsilon delta definition, this is the one that I'm talking about. The definition of a limit, the limit as x approaches c of f of x equals L, means that for each epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus c is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. So This is the portion of it that says x approaches c from either side, and this is the portion of it that says f of x is arbitrarily close to L. Now there's two funny variables in here. There's the epsilon and the delta. And one thing that is important here is there's some different language used. We say for each epsilon greater than 0. So epsilon is arbitrary. And in order to use this, the statement in the definition must be true for any epsilon. You should be able to choose any epsilon greater than 0, and you can find a delta such that all of this works. Delta can be chosen. So notice that it says for each epsilon there exists a delta. So basically what you do here is you let epsilon be arbitrary and you choose a delta that makes it all work. So epsilon is arbitrary, but delta can be chosen, and you usually choose it based on the epsilon. Now all these values are really, really tiny positive numbers. So some examples of something that would be an epsilon or a delta might be 0.004, 0.0004, the tiniest number you can possibly imagine that's still positive. There are two basic types of problems that you're going to see that come from this epsilon delta definition. So the first type is something like this. It says, given that the limit as x approaches 2 of 2x minus 1 equals 3, we're going to find delta such that the absolute value of 2x minus 1 minus 3 is less than 0.01 whenever the absolute value of x minus 2 is between 0 and delta. So in this problem, if you kind of fill in the pieces, this is the f of x minus L less than epsilon, and then this is the absolute value of x minus c less than delta. So we are given that our epsilon equals 0.01. It's got to work for every epsilon, so might as well work for a specific epsilon. And we need to find a delta that makes the definition work for this epsilon. Okay, so filling in all the pieces, f of x here is 2x minus 1. The L is going to be 3, because that's the L right here. The epsilon is 0.01, and the C is 2, and we need to find delta. So I'm going to work backwards in order to figure out what the delta needs to be. So I'm going to start with the absolute value of f of x minus L is less than the epsilon that we're given, and we're going to work towards finding the delta that we need. So we're going to start with the absolute value of 2x minus 1 minus 3 is less than 0.01, and we're going to work back to the absolute value of x minus 2 being less than something. We don't know what yet. So starting off with this side right here, if I combine the negative 1 and the negative 3, I get the absolute value of 2x minus 4 is less than 0.01. And I'm going to try to extract the x minus 2 from this. So the first thing that I'm going to do is observe that I can factor a 2 out of 2x minus 4. And then I'm going to use the rule that says the absolute value of a times b is equal to the absolute value of a times the absolute value of b. And I'm going to break that 2 out of that absolute value. So we got the absolute value of 2 minus the absolute value of x minus 2, and the absolute value of 2 is just 2. Now I'm almost there. I have 2 times the absolute value of x minus 2. I want to get this absolute value of x minus 2 by itself. So the easiest way to do that is just to divide both sides of the inequality by 2. And when I do that, I have that the absolute value of x minus 2 is less than 0.01 over 2. And you could write it like that, or you can simplify that. That's 0.005. Now this is the delta that I need because I have the absolute value of x minus 2 less than a number. So the answer to this problem is that delta is 0.005. So let's do another one of these. It says given that the limit as x approaches negative 1 of 3x plus 2 is equal to negative 1, we're going to find delta such that the absolute value of 3x plus 2 minus negative 1 is less than 0.01 whenever the absolute value of x minus negative 1 is between 0 and delta. So again, I'm going to fill in what I know. Coming from this portion right here, I have that f of x is 3x plus 2, and L is negative 1, and epsilon is 0.01. And coming from this portion right here, I have that C is negative 1, and we're finding delta. We don't know what that is. Now, it's just a coincidence in this problem. L and C are the same value, so don't let that throw you. But we are still trying to start with f of x minus L less than epsilon and get to the absolute value of x minus C is less than some delta. So I'm going to start with what I'm given. 3x plus 2 minus negative 1 less than 0.01. So that's really 3x plus 2 plus 1 less than 0.01. 2 plus 1 is 3. And I can go ahead and pull out the 3, and you know that it's going to be a positive, so you can absolutely do that in one step. And then here I'm going to have, I'm going to just change this back to x minus negative 1 because it fits my form a little bit better. And then I'm going to divide by 3. So coming up over here, I have that the absolute value of x minus negative 1 is less than 0.01 divided by 3. Now 0.01 divided by 3 is not a pretty terminating decimal. You could actually choose any number that's smaller than it. Most people tend to just say, okay, I'm going to let that be my delta. So this is actually 0.03 repeating if you find the value of that in decimal form. But you could choose any number that's smaller than that. So you could just lop off the last half of the decimal right after that first 3 and let your 0.03 be your delta. It doesn't matter as long as it's less than or equal to 0.101 over 3. That's kind of the upper bound for delta. You could choose anything smaller than that if you want to. Now this is the other type of problem that you will see with epsilon delta, and this says use the epsilon delta definition of a limit to prove that the limit as x approaches 1 of 5x minus 3 equals 2. Okay, so we're trying to prove that this limit has this value using the definition. So remember the definition. Let's go back to that. So this is the definition of the limit as x approaches c of f of x equals L. So we're trying to prove this for our function that we have here. The limit as x approaches 1 of 5x minus 3 equals 2. So whenever you're proving a for each statement, you have to start off with assuming that epsilon can be any value greater than 0. So the very first step of our proof is that we are going to let epsilon be greater than 0. Always put that. If you have one of these problems and you're trying to take a test with one of these problems on it, if you don't know how to do anything else, write let epsilon greater than 0 and you'll get at least 2 points. The next thing is we need to talk about all of the different pieces that we're trying to put in place here. So in this problem, we're not given an epsilon. We have to assume that, or we have to prove that it's true for any epsilon. But let's look at the pieces that we do know. We do know that our c here is going to be 1. We know that f of x is going to be 5x minus 3, and we know that L has got to be 2. Okay, so whenever you have a proof, if it says, if you're trying to prove a theorem, if it says the word if, that's something that you can assume. So we're going to assume that 0 is less than the absolute value of x minus c, which is 1, is less than some delta. We're going to figure out what that delta is in a minute. And in the middle here somewhere, I'm going to do a lot of work, but our thing that we're trying to prove is the then part of the statement. So the then says that the absolute value of f of x minus L is less than epsilon. So I'm going to come down here, I'm going to write then. The absolute value of our function was 5x minus 3. So I've got the absolute value of 5x minus 3 minus L, which is 2, is less than epsilon. And that's going to say that, therefore, according to the definition, the limit as x approaches c of f of x, or sorry, of x approaches 1 of 5x minus 3 equals 2. Okay, now you're looking at this and saying, why am I starting with my goal? We are kind of putting the cart before the horse a little bit, but we're going to do a little bit of background work and figure out what needs to go in the middle here. So I'm going to take a similar approach to what I started with before, and I'm going to do some scratch work. I'm going to find the delta that I need by working backwards. So I'm going to start off again with f of x minus L, and I'm going to try to get to that x minus c. So I'm going to start off with the 5x minus 3 minus 2 less than epsilon. That's 5x minus 5 is less than epsilon. If I factor out the 5, I get x minus 1. And then now that I've got x minus c, I'm going to divide by 5. So I get that x minus 1 has to be less than epsilon over 5, and we're going to let this be our delta. So coming back to the other side, where my actual proof is, I'm going to write delta equals epsilon over 5, and then I'm going to fill in the work to get from this point down to here. So I'm going to show that this has to be true. So I'm going to start off with 5x minus 3 minus 2, and I'm going to observe that that's equal to 5x minus 5, which is equal to 5 times the absolute value of x minus 1. And then because I know that the absolute value of x minus 1 is less than epsilon over 5, we can say that that's less than 5 times epsilon over 5. And that gives me epsilon. So if I follow the chain here, I've got the absolute value of 5x minus 3 minus 2 is less than epsilon. So those three pieces right there give me what I need, and I am done. Now this is just a bit of a stylistic thing. When you're done with the proof, it's not a bad idea to just draw this little box and show that you are done. Now proving things is different than just answering a question in mathematics where you're having to find a value or solve. In this problem, everything on the left-hand side of your screen here is the answer. Okay? If you're trying to prove something, this is what you want to have as your answer. You will have at least one of these on your first test, so do not neglect to study this.